Let me give you an example of where I personally used histograms in the material science and engineering research that I conducted. So in the work that I did in the laboratory that I was in our laboratory, we had a homemade laboratory device, which consisted of a vacuum chamber and two copper electrodes, one that came in from the top and another one that came in to the vacuum chamber from the bottom. And you can see this whole device sits inside of what's called a load frame. And what a load frame is this like top here, this hammer top, slowly presses down and it applies pressure to anything that's between those two copper electrodes. So looking inside the chamber, this is what you would see. So you can see a little bit of the copper electrode here, and we had a few graphite spacers. And right here in the middle is where we'd have a graphite die and two plungers going into the top and the bottom of this graphite die. And there's a little hole in the graphite die, and that is for a thermocouple, which is another word for a thermometer, to plug directly into it. So I could read the temperature of the die. And so what I would do is I would take a powder of a metal or a ceramic and load it into the die and put the plungers in on the bottom and put the plunger in on the top. And this assembly would then go right here inside the chamber between the graphite spacers and between those two copper electrodes. And because the graphite die was positioned between two copper electrodes, we could pass electric current through the system. And when electric current meets resistance, it creates heat. So by controlling the electric current, we could control how hot the die got. And so the purpose was to take that loose formed powder and heat it up and apply pressure to it. And in a matter of about 15 minutes, that powder would get compacted into a fully dense coin shape. So this is a picture of what that powder looks like once it has been densified. And to give you scale, this is a picture next to an American quarter. And then I would take pieces of this, really small flecks, little crumbs, and put them in what's called a scanning electron microscope. And the scanning electron microscope lets you see features in the powder, as well as the fully dense experimental sample at sizes that the human eye cannot possibly see. So here on the left, you can see that the powder is composed of these small round circular particles, spherical particles, and they kind of vary in size a little bit. But once you apply heat and pressure to these, they change. So instead of these nice round spherical shapes, they become these very strong angular shapes. These are called grains. And the spaces between the particles or between the grains is gone. So that's what I mean by fully densified. Okay, so how does this relate to histograms? Well, using some computer software, I would take a scanning electron microscope image, micrograph, and I would scale the image using a scale from the microscope itself, and I would draw lines across each grain. The computer would then take the length of the line that I drew across the grain and translate that into a length in nanometers, because of this scale. And so for every line that I drew, it would create a number, and it would save all of those numbers into a data file. And that's kind of what you're looking at here to the right, is there was one grain that measured 32.6 nanometers, so a line that was that long, another one that was 48.5, 54.4, 56.9, and so on. And I had maybe 325 grains that I drew in this one image. So minimum size was 32.6, maximum size was 496.6. So what you can do is you can take all of this data, this quantitative data, and make a histogram. So down below, here is a histogram of that image. And across the horizontal axis, this is where we have grain size. And grain size, remember, is the size of one of those angular pieces in the image. And frequency is the number that were counted. So with a histogram, if you count the number of objects that were between 0 and 50 nanometers in size, I had about 11 of them in the image. For grains that were between 50 and 100 nanometers in size, I had maybe almost 70 of them in that image. And in grain sizes between 100 and 150, it was maybe a little over 90. From 150 to 200, I had just under 90, and so on. So remember what I said about histograms, is that the bars have equal width, but they are a width that you calculate. And so you'll notice that the width of each bar is 50. So 50, 50, 50, 50, 50, and so on. And the number of bars that I've got, the number of classes that I have, are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 bars, or 10 classes, each with an equal width of 50. And this value of 10 and this value of 50 was something that I calculated. Okay, so this shape represents the size and the behavior in this image up above. So this image was taken of a sample that was heated to 650 degrees centigrade. All right, so what I wanted to do is I wanted to see what the effect temperature had on this powder. So I would take that powder and subject it to several temperatures. So I'd do one experiment where the maximum temperature was 550 degrees centigrade. I did a second experiment where the maximum temperature was 650 degrees, a third experiment at 700, a fourth experiment at 800, and a final experiment at 900. So I did 5 experiments, and I measured the grain size for each of the samples that I made. And what you see here are histograms for grain size at each temperature. So this is a histogram for a sample that I made at 550 degrees centigrade. Here is another histogram for a sample that I made at 650 degrees centigrade. This third one, this is a third sample. This is the histogram of a third sample for a sample made at 700 degrees centigrade. Here's another one for a sample made at 800. And here's another histogram for a sample made at 900. Now, if you were just looking at the images themselves, it might be hard to discern a pattern as far as the effect that temperature had. And you might be able to get a sense that the grain sizes are increasing, but when you take that data and you take those pictures and you make histograms, it becomes more clear what's really going on. So what you can see is that the distribution of grains, the sizes of the grains, has this very symmetrical shape, and it's centered somewhere around 150 nanometers. So that means the average grain size was about 150 nanometers. And if I raise the temperature from 550 to 650, the grains didn't grow very much. Okay. The average is still maybe a little bit more than 150, but the distribution of the sizes looks almost exactly like this one. And if I raise the temperature even higher to 700 degrees, it doesn't look like the grain sizes are growing that much either. But you can see as I transition from a maximum temperature of 700 and I go up 100 degrees to 800, now there's a significant change. The grains that didn't grow started growing at this temperature. So you can see this histogram, the peak of the histogram is not only moving to the right, moving towards larger grain sizes, but you'll notice that the width of the histogram is also getting wider. Here it's rather narrow, rather narrow, rather narrow, but here this is significantly larger or significantly wider. And if I go to an even higher temperature of 900, all right, you can also see that this histogram is continuing to shift to the right. The grains are growing, they're getting larger, and the distribution of those grain sizes is widening. All right. So for me as a materials scientist and engineer, I wanted to find the maximum temperature to do an experiment without grain growth. So if that was my goal, was to get the highest temperature without grain growth, what temperature would that be? 550, 650, 700, 800, or 900? So the answer is 700, because at 700 degrees centigrade, the grain sizes still remained roughly the same. It was when I went from 7 to 8 that the histogram started to shift to the right and shift to higher grain sizes. So 700 degrees is the maximum temperature I would want to go in. And that, for me as a scientist, as an engineer, tells me something important and that I can build off of to make more discoveries. And I did that using histograms. Okay, so that's a good place to stop before we actually get into the explanation of a histogram.